Today we are going to look into the last part of chapter 5 on the frequency analysis of signals. So this last part is on an inverse system or deconvolution. We are trying to find a system that can inverse or revert the effect of a filter. This filter can be a physical filter. For example, it can be a communication channel. So that is something that is unavoidable. It will happen to the signal. Sometimes it will give some bad effect. We want to avert that effect. So we design an inverse system. We're putting another filter to remove that effect. And in the time domain, it looks like we are getting a signal of Y, but we're trying to recover the original signal X. Let me draw here. In the time domain, it looks like we have observed the signal Y, Yn, but we want to find out what is the original signal X. For example, that can be a communication channel. So the channel itself is any transmission media. And we don't know that. And what we have here is observe the signal Y. Now the Y can have a lot of this filter edge effect, and it's corrupted, either it's corrupted or distorted version of the original signal X. And we want to recover the original signal Xn, let me call it X hat, estimate of X. So we have another filter here called H prime. This H prime is an inverter. In time domain, we can think that as a deconvolution. We're trying to find X convolved with Y equal to X convolved with H equal to Y, but we have Y, and if we have H, if we know some H, if I want to deconvolve and find the original signal X. In many practical applications, we are given an output signal from a system whose characteristics are unknown, and we are asked to determine the input signal. We need to find something from the input signal. Input signal is not known, it's not observable directly. Channel distortion and a need for a corrective system. So this is an inverse system. Now, what is channel distortion? Channel distortion, as I said, let me use this. For example, communication system is I have the signal coming here, go through a channel, and then I have the receive signal. This is the receive signal. Now the channel, for example, the channel is very simple. We have a wireless communication channel, for example, and then the signal coming in, because it goes through the media. Media is the free space propagation, so it can have an impinging waveform. It may have another reflected waveform from the ground, from other buildings. So these are this one and this one. Those are the multipath. This multipath has a delay effect. So the channel itself is a delay effect. So we have looking to this Hn in the time domain. So we got an impulse here, which is the first impinging wave. Then we have some delay effect. These are due to those two multipath. So if I have in the time domain those delay effects, so I have not only H0, but I have H1, for instance, I have H3, for example, H2 is 0 here. The signal Xn will go through a finite impulse response, right? This is a finite impulse response. The impulse is not just a delta, but it has some other parts here with a support that is expand just one time instant. Then I have the received signal at Y. If this is FIR system look like that, it's a delayed element here. What will that give us in the frequency domain? In the frequency domain, that will give us some frequency selectivity. So in the frequency domain, roughly speaking, F H omega instead of being flat, it will have some effect, maybe like this, for example. So this is the frequency selectivity. So some frequency will be emphasized, some frequency component will be de-emphasized. And that is a frequency filter filtering the input signal X. And then what we want is I want to have an equalizer. Now this equalizer, I want to multiply, for example, let me call this H prime omega. And the effect is, let me just draw this way. The effect is H prime multiply by H, then I will have a flat line across all frequency. And that's what an inverse system will do. Because it does that, we give a name called equalizer. We equalize the frequency component, make every component of the frequency part equal. It's evenly distributed. Right? So that is an equalizer. We have many good use of an equalizer, and we have many different ways we can deal with that. Okay, so an inverse system is a corrective system that has a frequency response, which is basically the reciprocal of the frequency response of the system that caused its distortion, like we seen on the previous page. Deconvolution is the inverse system operation that takes Yn and recover Xn. So the effect in time domain is a deconvolution. System identification is another kind of deconvolution. Now this deconvolution here is we know Yn. I also estimate a system. I want to find what is my input X. What is input X? So we do a deconvolution. System identification is that if I know Y, I observed Y, I know what is the signal to the system. I want to find what that system is. That is, we call the system identification. We have done that before. We're solving for a difference equation. Is that we know the input X, we observe the output Y, and we putting everything into a difference equation. Then we solve for this difference equation, find out what Hn equals to. That is system identification. System identification, we can go ahead and find a little Hn in time domain, or we can find capital H omega in the frequency domain. Either way, we can find the system. We can identify the system. A system is said to be invertible if there is a one-to-one correspondence between its input and output signals. So an invertible system represents as a linear operator T. Then its inverse system is T to the power -1, and it's inverse. And we want to emphasize that because in frequency domain, okay, T multiplied by its inverse system, which should give us identity. That should be one across all frequency. That is a constant. One is not a function of frequency, right? So it's constant across all frequency. Right, so the signal go through my inverse system. So we have this inverse system, that's an operator on the output signal, Yn. So that is my inverse system operation on Yn, which is the operation on Xn. And that should give me original signal Xn. So the output Wn should be equal to Xn. We recover the original input signal. Therefore, T is indeed an inverse system. We're putting this in the block diagram. So Xn coming in here, go through a direct system as T, become signal Y. Y go through an inverse system, T to the power -1, and give me the final output to Wn. And we want to have Wn equal to Xn. Therefore, the entire thing in this dotted box is identity system, right? Everything, this is T -1 times T, those two operators. What should that be? Well, in the frequency domain, that is 1, as we said here, that is 1. What is this in the time domain? This identity system, if I'm trying to look entire system, we call this entire system H. This is the entire box. What is that? For an identity system, that is quite straightforward, right? We do an inverse Fourier transform. What is inverse Fourier transform of a constant, especially 1? That should be equal to delta n. Delta n, it's just a delta function. Well, indeed, xn, the input signal, convolved with a delta function, that gives me xn. So the output is still xn. Therefore, that is the identity system. The LTI system T has impulse response Hn. The inverse system T to the power -1 has impulse response. We call it H sub I. Because Wn is equal to Xn, so Wn is system X, signal X go through system H, go through system H sub I. So those are the two convolutions. Now convolution, we can associate these two convolutions together. Therefore, these two give me a combined system. That is the delta function, delta n. In frequency domain, we have already seen that capital H Z times capital H sub I Z equals to 1. That gives me an identity system. Therefore, H sub I is in the inverse, 1 over capital HZ. If Hz has a rational system function, which is the usual case for any system that is implementable, we can draw the schematic for that with A's and the B's. Those are the polynomials. The B's on the numerator, that's the feed-forward network, right? Feed-forward, we have delayed tap. And the AZ on the denominator, that's the feedback loop from the Y, and it comes with a delay, with few delays and coming back. We should know this we should be very familiar with these. If this is the case, a rational system function, then the inverse system can be easily expressed. We just flip the numerator denominator, so that is A over B, which means that the zeros of AHZ become the poles of the inverse system, and vice versa, right? Because I change numerator to denominator, denominator to numerator. So the zeros and the poles are exactly exactly change their positions from the direct system to the inverse system. If HZ is an FIR system, HIR system meaning that the system has only numerator without any denominator. So HZ equals to BZ. This is FIR system, finite impulse response. That means I only have zeros, there is no pole. Then H sub IZ, that is in the form like this, 1 over BZ. Everything is on the denominator, there is no numerator term. So H sub IZ is an all-pole system, and vice versa. In the time domain, we have this expression. The convolution of H and H sub I is delta function. Okay. We assume the system and its inverse are causal. For any practical system, it's a causal system. Causal system that the system is not defined when n is less than 0. Then this question simplifies to that. This is a causal system. It's either not defined, or when time is less than 0, everything is 0. You just make everything 0. That's a causal system. So the causal system that we have this convolution is k from 0 to n. We have that. This is delta n. Now, how come it comes from 0 all the way to n, not to infinity? Well, we are not only need to taking care of one system, H, but we also need to taking care of the other system, H sub I is also causal. So therefore, this sum is bounded by two ends. either 0 or the current time n. So it's from 0 to n. Given that, we can calculate h sub I iteratively. So for n equal to 0, we find out h sub I 0 equal to 1 over h 0. So that is simple because h 0, h sub I, n is 0. So that's negative k, which is also 0, k from 0, equal to 1. And so we find that. If n is greater than equal to 1, then h sub I n can be obtained recursively using this format. I think there's a typo in the textbook. So this is correct, because from here, all we did is we just taking one term out of the summation, which is k equal to 0 plus k from 1 to n hk times h sub I and subtract k equals to delta n. Right? If n is greater than or equal to 1, this part becomes 0. Therefore, you move this to the right of equation, and we find out HIN can be expressed in this form. And that can be easily calculated for the inverter system. Okay. We have other ways to do this, to find this equalizer. Especially, there is a method for advanced digital signal processing. It's called optimum linear filter. Let me just start it. We were going to get back this later, at a later time, to see how to solve for an optimal linear filter. So the optimal linear filter is that I have a data, that's the input data, x1 to xn, that I have go through a finite impulse response filter. This FIR filter with parameters f1, f2, all the way to fn, we have the output, which I call this y hat. This is the output of this filtering. So in the time domain, if we look at this equation, using this pen, this equation here, this is a convolution. This is a convolution of x with f, and we got the output of y. Now, our job is to find those coefficients, f's, and such that we have a very nice filter for all the x, I can estimate a y. We get a y for our purpose, and that can be extended very easily to an equalizer, for a system inverter. So we will see that detail later, but right now we just get a concept what we are trying to do. And this y hat will compare with a true y. That's a desired response. I want to make sure this equation will be equal to the true y. Therefore, there is an error. The error is between the desired response and the response from the filter. So that is y subtract f times x. F is the coefficient of my filter. X is the input signal. If I'm writing that into a vector form, so F is this column vector, X is column vector. I should put a Hermitian here. So I'm doing F transpose. If F in general, that's a complex number, I do a Hermitian. Those F Hermitian times X, that's a scalar. Subtract Y, that's the error. Now what we want to do, we want to minimize the error. But the error can be positive and negative. Both will give us a bad effect. So I want to minimize absolute value of the square. And then I may need to have a lot of input signal. So I want to minimize the expected value of this E square, which is in the complex format, that expected E conjugate times E. We want to minimize that. Minimize that with respect to variables f's, with respect to variable f's. This is called the minimum mean square error optimizer, or the linear filter. And that can work very well to find a best equalizer, to find the best invert system. And we will see that later on. So let me get back to our chapter. Okay, so I'll just leave it there. Give us a good feeling, a step, beginning step. Then we will revisit that idea for optimal linear filter later on. Now we are getting into a concept which is called minimum phase, maximum phase, and a mixed phase of a system. Phase is another part of the filter. We are not only looking at amplitude, but we also want to look at phase. For amplitude, we know we can have a low pass filter, high pass filter, band pass filter, and that is all looking at absolute value of H, the amplitude. What do you want? What kind of signal of high frequency or low frequency you want to emphasize? But there is also a hidden element, which is the phase. We don't really see that. When I plot this image, we have H absolute value. So for low pass filter, it goes like this, from 0 to pi. But there is also another element we are not looking carefully, which is the phase, which is angle of H omega. We said something about the phase of a filter. When we mentioned that, we mentioned something about a linear phase, right? We want to have a linear phase system. We also mentioned the group delay. Group delay is the derivative of the phase. So in this case, if it's linear, then the group delay is a constant. So now we look into this phase issues to see how we can relate this to a system and what kind of effect that it will give us. I have two systems here. Two systems is H1 and H2. It's given on this page, those two examples. H1 is in the Z domain, 1 plus half times Z to the power negative 1. H2 in the Z domain is half plus Z to the power negative 1. So what is in time domain, H1n and H2n? In time domain, right, this is delta n plus half times delta n minus 1. This is half plus delta n plus delta n minus 1. So on a picture, we see that the first H1, it looks like in time domain, that is a delta here. And then I have a half here. This is 0. This is at 1. For H2 time domain, we have a half here. This is 0. Then I have a 1 here at time 1. This is a half. This is a 1. This is a 1. This is a half. Right? It's a delay system. We have a delayed tap, a finite impulse response. All right. So in the frequency domain, we will see that this delay element will give us frequency selectivity. So capital H2, we will have an angle. That angle is not 0. We also notice here, now compare these two systems. Which system or which filter is a better filter? It's hard to say, but just by looking at those two delta functions, we see that, well, maybe H1 is better because I have a delay path here is smaller. I want to concentrate all the energy at this non-delayed path, or we concentrate the energy of the filter as much as close to 0. Therefore, I don't have a heavy delayed tail, right? So you have the input Xn, you give a Yn output. You don't have too much of the delay effect. Now compare with the second one, the regular incoming signal through this filter, Xn becomes half of Xn, but you have a delayed term. This delayed term is relatively large. You have a large delayed, or it's a large tail there, tail effect. And then it seems that if I have the energy of the system kind of dispersed into a large time, a large delay, maybe it will give me a worse effect on my input signal Xn. So we keep that in mind. let's continue to examine H1 and H2. All right, so what is the amplitude of the frequency domain signal like this and this? Absolute value of H1, absolute value of H2. To calculate that, let me just work on one part. Let's see H1 omega. H1 omega is here is 1 plus half. And then we have here is e to the power negative j omega. Right? And this will give us 1 plus half a cosine omega subtract j sine omega here. Oops. And so the real part is this. And then we have the imaginary part here, j omega. To find the absolute value of h, that is equal to 1 plus half a cosine omega square plus sine omega square, and then take the square root. So that we have, let me just do a few steps here. That's 1 plus cosine omega plus 1 over 4. Oh, excuse me, have a half here. I have a half here, so this is 1 over 4 here. So 1 over 4 cosine square, cosine omega square, and plus 1 over 4 sine omega square, and then take a square root here. That will be square root of 1 plus 1 over 4 plus cosine omega. All right, so that's what we have here. The amplitude is equal to that. Now, if you calculate the absolute value of H2, you get the same result. It's 5 over 4 plus cosine omega square root. From the amplitude part, I cannot see any difference between these two filters. However, from the phase element, if we're looking at the angle of H1 and H2, they are different. Now, how to look at those two phases? Well, the phase is, in this case, is you can either working directly on this real part, imaginary part, or I can do is H1 omega equals to e to the power j omega times 1, okay, times e to the power j omega plus 1 over 2. Okay, like this. I'm simply moving e to the power negative j omega to the front out of this parenthesis. So we calculate the angle of H1. So the angle is the first, this part, the angle is negative omega plus the angle of e to the power j omega and a half. Right. Now the second part here is a cosine omega plus sine j sine omega plus half angle of that. So that is equal to negative omega plus. And to find this phase, well, it's arctangent. Arctangent of the imaginary part, which is sine omega, over the real part. Here is 1 over 2 plus cosine omega. Okay, therefore I got this result. Result is here, exactly here. If we calculate the angle of H2, we find out it's different. It's different. We got some part here, it's different. Let me rewrite those two phase values. Those two phase values, if I plot on the image, this image is with respect to frequency omega. The y-axis is the phase, the angle of H1 and angle of H2. We find out those two are different curves, and those curves are not linear. They have this curvature effect. It's not linear. The first one is look like this. It goes through origin, and it will end at 0 when omega equal to pi. The second one go from origin, but it will end at negative pi when omega equal to pi. We call the first part, we call that a minimum phase system. A minimum phase system is that we only looking at those two extreme ends at frequency pi versus frequency 0. If the angle at frequency pi subtract the angle of frequency at 1, at the angle at frequency 1 equal to 0, we call that a minimum phase system. If the angle of the system at pi subtract the angle of system at frequency 0 equal to pi, we call that a maximum phase system. Okay. And for the real valued impulse response, if impulse response Hn has all these finite impulse response, for example, that I have all these H1, H2, H3 are real numbers, then we know the Hn is a complex symmetry. It's a complex symmetry. Therefore, it has to go through the origin. The phase has to go through the origin. Therefore, the angle of H when omega equal to 0, that is angle of H0 equal to 0. That has to go through the origin. To look at the effect of the phase, let's look at how to find this phase angle. And we are using a picture to find a phase angle in this general format. Then we look back into our specific examples of H1 and H2 to see why we call that minimum phase and maximum phase. So in general, a linear time invariant system can be expressed in this rational format. So Hz, we have here as a polynomial on the numerator and a polynomial on the denominator. So we got the zeros and the poles. The phase response of a rational Hz can be written in the following. So the phase is the angle of H omega. We are looking at the phase first, this term. So we multiply by this term of the entire thing of these two product multiplied by this. This is a constant. So if I'm calculating the phase, so I'm putting the phase of this constant first. Right? It's not a function of omega. So the phase itself is a constant. Then plus the entire phase of this rational format, which is a product of all these zero terms and a product of these pole terms. Okay. Similarly, we can separate these. This is an angle of the numerator, the zero terms. Subtract, because it's division. So subtract this angle of this denominator terms. And then it's a product. For the angle, it becomes a summation. So summation, and then we calculate the angle of all these individual terms. Okay, so let's just look at the first part here. So what is the angle of this? This is, as we did before, now 1 subtract C sub n times e to the power negative j omega, that is equal to e to the power j omega subtract c sub n times e to the power negative j omega. Right, this is the same as in the box. Now, if I put in an angle here, so that will be this term. So that will be the angle of e to the power j omega subtract the zn, subtract the angle of e to the power j omega. And what is this? If I'm looking that into on the z plane, a complex plane, now the red one, these are the zeros. The blue dots are the poles. So we are looking at those. This one is okay. Let me using the previous. Let me putting no space here. Let me just write on here. So the point here, it go on the unit circle. This point is e to the power j omega. The point here is Zn. Right. So what is this angle? This angle is you have C e to the power j omega subtract zn. So we are looking at a vector that is on the complex plane, that is a vector pointing to c to the power j omega, that this vector, right? And then in this case, that is this vector, and then we subtract another one, which is just e to the power j omega. The other one is this point, and in this case, the angle is 0. This angle is here. Let me exaggerate here. So this is that part. It's this angle. The second one is this angle here. It's zeroed. It's 0. And the same thing, same as if you go on this unit circle, you will also have this effect. Okay. So now to calculate the previous one, we have another effect which is coming from here of a pole. So if you combine these two, remember that in theory, we have the same amount of zeros and the poles. If you don't show that pole, the pole is simply deformed onto the origin. That is the middle of your Z plane. But we have those two parts. So if I have this part, I will have another part here. Therefore, the poles is similarly, I have e to the power j omega subtract Pn, subtract an angle of EJ, this part, right? So if I compare this, I'm using another. Okay. If I compare this one with this one, subtract, so that will be canceled out. So what's left is only the angle between your current point to the 0 and the angle of the current point to the pole, which is here. This is the here is the angle. That's between, we want finding the angle of this vector. Also the angle here. That's how we see in the distance of that. And we are using that to find the phase. So in general, that's how we see how to visualize this angle. Now let's look back to our case. Our example is simpler. Now let's see if I can, using this to explain the minimum phase, maximum phase issue. So in this case, I have the unit circle here. I have two poles for my system. Let's take example of H1Z. What are those two poles? Excuse me, the two zeros. It's an FIR system. The poles are deformed onto the origin. We don't have denominator, but we have FI system. We have zeros. Right? For this system, H1, I have a 0 at 1/2, negative 1/2. For H2, I have a 0 at 2. Right? These are the first order. These are the system, the FI system. I only have one delay. So for H1Z, I have a 0 here at negative 1/2. For H2Z, I have a 0 here at negative 2. This is the Z plane. Now, if I have a signal and travel along on this unit circle, so that will give me a frequency domain signal, which is H omega. With this is my omega value. This point on the unit circle is e to the power j omega. Focus on the angle of H1. We have here, this H1 is equal to that's e to the power j omega times e to the power negative omega times e to the power j omega subtract Z1, right? Z1 is negative 1/2. So we have that. This is what we have right here. Right here. And therefore, the angle of H1 omega is the angle which is negative omega plus this angle here, which is the angle of E j omega subtract Z1. Okay, so we are looking at those two parts. Now, if I am adding at this point, this is E to the power j omega. The first is the angle of this vector itself. So the angle is here. This angle is omega. The second angle is the angle between this point, E to the power j omega, and the zero, the first zero, Z1. And it's pointing to this angle here. This angle is right here. This angle is right here. That's the second part. The second part is the difference of two complex vectors, E to the power j omega and then Z1. Therefore, it is this line here. This is the line here, and the angle is here. The difference between these two, from geometry, we know this is the angle, it is right here, right? So the angle, the first angle subtract the second angle, that's the angle right here, in here. And we have a negative sign. So actually it's negative sign, the negative of this angle between this zero and the origin is right here. Okay. So with that, now let's check what will be the largest time of this angle in the absolute value sense. Is when I travel on this circle, when I get to somewhere here in the middle, right? And it should be somewhere here. Somewhere traveled here, and it gave me a pointing here and to the origin. So this angle is the phase. Well, actually we putting a negative sign here. And that will be, in the absolute value sense, that will be the largest. Now, if I starting from zero, which is the phase angle is 0, omega equal to 0, then because it deformed into a line, therefore this phase is 0, right? This angle is 0. If I travel all the way to pi, same thing. I got this angle is, you squash that back into 0. So indeed, we got those two parts, that is 0 and a 0. Now in the middle, when I travel that on a positive, when omega is positive and everything, we have this angle and everything is a negative sign. Because we got a negative sign here. That's negative omega subtract the angle between EJ omega and Z1. We got a negative sign here. So that's all, everything is negative. Similarly, if I travel on the other side of this unit circle, I got a positive result. I got a positive. And then if we go back to negative pi, it will deform onto 0. So indeed, the phase should look like that. Compare that with H2. Let me very quickly work on the second part. For H2, now if we are looking at this image here on the Z-plane, we have a 0 that is outside in a circle. It's here at the -2. Similarly, when we calculate the phase angle at any point on the unit circle, which is e to the power j omega, then what we did is we are finding this angle. That's the difference between here and here. So the angle is this angle. And of course, you take a negative sign. So same thing, if I starting from point here, when the phase is equal to 0, then this angle is 0. So starting from 0. When I move on, when I have a positive omega, then I have this angle, because it's negative sign, everything is negative. When I travel all the way to here, to pi, now because those two edges, they are spread, those two. So the angle is really, we check this angle is pi. This is the highest I can get. pi. And then the difference is pi subtract 0, that's pi. And then I travel back as I'm going along this line, and it's positive, but eventually it will become 0 again. So that is the maximum phase. The maximum phase is because I have a 0 that is also in a circle. So you travel along this line, you find the angle. When you add a pi, you completely different side of my point. So the angle has the maximum, has pi. So that's how we verify that, how we visually to find this phase that is indeed, we have a minimum phase changing from 0 to 0. And this is the maximum phase case, we're changing from 0 to pi.